So for the bulk of our lesson today, this is the data from the oranges. Everybody remember the hand putting oranges in the scale? And then the scale went up. And this was the same data from 2 lessons ago, right here. Same data. Now what I've done for you is we need to get a line of best fit for this data. We estimated one. We looked at it and said, we drew one. We said this is about the slope. This is about the y-intercept. You're going to get the actual line of best fit today. And here's what I did for you. See this link right here that says Desmos? That is linked to the table already put into Desmos for you. So what you need to practice doing with your partner then in Desmos is using the line of best fit equation on the next line. And if you don't recall, you do have those notes I gave you last class, but it's like y1 squiggle m x1 plus b. Okay? That squiggle's the top left with the shift. Top left of your keyboard with the shift. So what you're going to do right now is you're just going to get the equation for the line of best fit on Desmos. Let's type in our line of best fit. Y1 equals, or squiggle for this case, because line of best fit, m x1 plus b. All right? This is on your Desmos cheat sheet if you need it as well. Here's what we're going to pull from this. We need to pull the slope and y-intercept. And what this then tells us is this line, and remember the line is the estimate. The line of best fit is y equals the slope is 0.216 and the y-intercept 0.345. So we worked on, last time we did this, I think we had a slope of 0.2 and a y-intercept of 0.3 when we just eyeballed it when we did it the first lesson. So this is pretty cool to see that we were pretty close. And next, I just want to summarize what this equation means in context. All right, oranges going in the basket. So what does the slope mean in context of those oranges going in that box? Raymer?
Every orange that goes in the box, the weight goes up by 0.2.
Yeah. So something like a weight of an orange. About, right? It's about 0.216. Were all the oranges exactly the same weight? No. Okay, and then the y-intercept happens when there's no oranges. What did that mean in context? When there's no oranges, why was there weight?
Oh, the weight of the box.
I want someone more than Raymer here.
The weight of the box.
The weight, yeah, the weight of the box. No oranges, there is weight there, that's the box. So again, all these actual dots here, those were the actual weights on the scale when the oranges went in. This line is the theoretical line of best fit for any situation of all the oranges forever. Okay? Does it look like the points are exactly on the line? Nope. That line is the line that best fits the summary of the data. So here's what you're going to do next. Make sure you have this written down on your notes because you're going to use it over and over and over for what you're going to do next because I can't stay on this view to do that. So everybody has that down? Y equals 0.2. Well, you should have it on your Desmos anyway. It's just the slope and y-intercept given to you down here on your Desmos.
What do we write in the table?
Well, I'm getting there. So, back to the presentation here. Over here, the estimate. Is the estimate the actual values or the values that are on the line of best fit?
Values on the line of best fit.
Correct. So, for over there, you're going to use that equation right here that we got, y equals 0.216x plus 0.345, and you're going to get estimate weights from your line of best fit. So what I'm going to do for 3 oranges is I'm going to put in 0.216 times 3, right? 0.216 per orange for 3 oranges, plus 0.345 the box, and I get a linear estimate of 0.993. You need to get the estimate for all the oranges. Again, that's what your theoretical line of best fit oranges would be using your line of best fit right now. I need you to fill out the table and stop. Fill out the table and stop. So for the rest of these, I got 1.209 for 4, 1.425, 1.641, 1.857, 2.073, 2.289, and 2.505. And just a reminder, the way I got these is I took my number of oranges and I threw it up into my line of best fit. So these are my estimates. These would all be on that line we found on Desmos. Remember, that line fit the data well, but was any of the data exactly on the line? No. So to decide if your line of best fit is good, we need to do something else. Well, it will be good. But to see how close the data trends with the line of best fit, we need this new piece of information. And this new piece of information is called the residual. So you're going to make a new column next to this data. And what this is called is the residual. And what I want you to do right now is make a connection to mean absolute deviation right here. So the mean absolute deviation was like on average how far away we were from the average, right? Do you guys remember that?
Yeah. It was the average of that.
And that was because we had one variable. Now we have two variables. You can kind of think of our line of best fit, kind of think of it as an average of the data, right? It splits all those points perfectly in half, kind of, right? So the residual is the distance that the estimate is away from the actual. So the actual is the actual dots. The estimate is the line of best fit.
Should we add more?
Well, we're not going to add. We're going to see how far away they are, we're going to subtract. And what we're going to do every time is actual minus estimate. Kind of remember that warm-up? Do you guys remember that warm-up? So we're going to do actual minus estimate. So I'll do the first one. I'm going to do 1.027 minus 0.993, and I get 0.034. That's the residual. That is saying the actual dot is 0.034 higher than my line of best fit estimate. I need you to do that for all of our data points for these oranges. Let's close. Let's get these residuals. So we're subtracting. I next got negative 0.047. Then I got 0.077. Negative 0.024. Negative 0.096. 0.042. Negative 0.056. And 0.064. So, all these numbers we just calculated, as a refresher, residual says this is how far away the line of best fit is away from the actual thing. Okay? Would you guys classify these numbers as big numbers or small numbers?
Small. Very large.
Small. So we could then maybe assume that these numbers are pretty close to the line of best fit then, right? We get these small numbers, that's what that would mean in context. What I would like you to do with your partner is find which data value of the actual is closest to the estimate and which one is the furthest from the estimate. And you can find these on your notes that you got in front of you. All right, y'all. Who can tell me which one fits the best and how you know? Eliana?
The closest one is number 6.
Number 6, okay.
Only 0.024 away.
That's only 24 thousandths away from the actual line of best fit to the actual data. Okay. So anybody else? Is there a better one? I don't see one closer. Do you?
No.
Is it easy to tell right here that this is for sure definitely the closest just by looking at it?
Yes.
I don't think so. It looks like 0.3 away or so. Aren't there other things that are kind of close? Like 8's kind of closest to that. 3's kind of close. Like I think at a glance you would need to look at the residual. Okay. At a glance, the residual is pretty quick to see what's closest. Okay, what's the worst fit then? Which piece of data fits it worst, Micah?
Number 7, which is 0.096.
Yeah, it's almost 1/10 off, isn't it? And again, who can tell me what's the reason that they don't all fit the line perfect?
Because it's the line. Because the oranges are different.
Yeah, they're not perfect, exact same oranges, right? It's the line of best fit for oranges, but there's some variability in their size. They're not all going to be exactly the same. All right. Here's what we've got to do next. And it looks different on the slide, but it's right in your notes. And I'm going to borrow someone's notes to get the picture for this. We are going to work on graphing our residuals. So I'm going to get a piece of paper on here. That's paper. And I'm going to grab the residual graph here. Oh, cover's in the way. Whoa. Okay. And, oh no, it's crooked. I gotta redo it. I can't do it. All right, so you're gonna take, this is gonna be your residual graph. Hey Bob, I need you to focus up for me. Okay? This is your residual graph. You're going to go and graph all your residuals on this next in your notes. So, for 3 oranges, how far off were we?
0.034.
So about a third, 0.034 would be right about there. So there's my residual graph for 3 oranges. So how far away it is from the actual, okay? You're going to do this for all of your residuals. That's what's next. Okay, so 4 is negative 0.45, so almost half.
What is 9?
Way there. 5 is 0.077. 6, negative 0.24. That one was really close, right? 7, almost negative 0.1, almost. 8, we were at 0.042, so just under half there. 9, a little more than half underneath. And 10, 0.064, a little more than half. And you guys told me 6 was the best. See how close that is to the x-axis there? And you guys said 7 was the worst. That's the furthest away. If our data was perfect with the line of best fit,
They'd all be on the line.
they'd all be on this line, right? Cool. That's everything we need to know about that. Next, we're going to practice matching scatter plots with lines of best fit to their residual scatter plots. So this right here, this is called a residual scatter plot. And let's make a big idea. The closer we are to the x-axis, what does that mean about our scatter plot in relation to the line of best fit?
The line of best fit fits well.
Well, not just fits well, but like all the data is close to it, right? The estimate and the actual close. What happens if we were all spread out kind of far? It could still fit it the best it can, but the data would not be that close, right? More spread out. So I'm going to hand you a card sort next. We already did all this. You're going to match the scatter plots with the residual graphs, all right? With your partner. So Micah says A and K he thinks go together. Let's take a look. And here's some things I like to point out. Look at these 2 points that are close to the line. Look where they happen. 1 and just after 4. So that's good. Also, my first 2 points are above. Check this out. Or my first 2, well, this first one's not even on there. Where's that one at? Above. Then this chunk that's below. Below. Above. That's another way you could look at it. All right.
We saw it kind of like they had the same pattern.
Same pattern. Okay, so there's A, K. Who's got B for me? What do you think, Stella?
B and G.
B, G.
NPC Elliot.
BG's what I got as well, Stella. Here it is.
Bye. Bye.
Okay, Stella, what made you think B and G went together?
Because on the line,
Yeah.
there are 3 points that match up exactly, and the same thing with on G, and they're the same points, which are 7, 8, and 11.
So you noticed 3 on the estimate fit the actual perfectly, and they show up right there on the x-axis? Okay, I think that's a great way to match those. Cool. So there's B. Next, obviously A, B, D. I mean C. Who's got a match for C? What do you think, Willett? I. Okay, let's take a look. Let's take a look. One thing I'm going to notice here, Willett. Do you see how right here there's 2 or 3 that are on or really close?
Yeah.
And those were over like 7, 8.
Yeah. 3 that are close and not really.
Okay, so do you want to give a next guess? That seems like a great mistake.
L.
So you're thinking L. Let's take a look. So as I look at these two, I like looking at those ones that fit perfect right there, right? Oh, check it out. Nice. I think that's the easiest reference, don't you guys think, on the x-axis? Okay, so that's C. Next comes D. Who's got a match for D for us? Raymer. You're thinking H, eh? All right, let's take a look at that one. Okay, Raymer, why did you think H? I got like 7 that are close or pretty close, right? And look at all those that were pretty close. Okay. I see Hadley.
We put J for a match for D.
Okay.
This is because of the scale. Because they both have decent scales.
Oh. But we're looking at how far away from the line it is, which, even though it's a big scale, like, right, 25 away is the furthest away. Right? 25 away would be the furthest away. So what you're going to want to match is furthest. It would not need to be the same scale because there was...
I know it would be the same scale. I feel like that would have the differences.
Okay, so J, though, only shows a couple in the middle being really close. Do you see that on J's residual? It only shows 3 in the middle really close on J's residual. So it doesn't work as the residual then. But I'm like that you're looking at the scale. That's good because the scales are different on a lot of these. That was D. Now let's look at E. Who's got a match for E? Yeah, Ellie.
J.
J. Let's take a look at E and J. So Hadley, I think you'll notice here. There's a similar shape, but here's what I'm going to point out. See these two, right? By the way, that's a bad line. That's not the line of best fit, right? That's a bad line of best fit. But check out those close to the line that they put down as best fit. It matches up there, right? Okay. And that means the last one has to be F and I. Let's take a look at those. And again, on these, I'd like to look at the one that's right on the line. Check that out. It matches up. You guys see that? Cool. All right, I'm going to put up our lesson summary here. We can plot them. We can see how far away we are. I need these back paper clipped in their stacks, and I need you to show me your lesson summary to get the homework going.